Hello and welcome to ABB Electrification webinar, which is CIBC CPD accredited on decarbonisation of buildings using energy measurement and analysis. My name is Nigel Thomas and I'm the UK Technical Promotion Leader, and I'm joined by my colleague today, Richard Quilter, who's a Technical Promoter for the London area. The learning objectives of this CPD give an appreciation of how energy is used today, with a look at global megatrends and an assessment of energy efficiency standards. Also, to give an understanding of factors driving the net zero carbon agenda and subsequent development of energy management and verification technologies. We will also look at digital twins and how digital twins are contributing to the future design strategies to reduce carbon. We'll look at how energy is used today, urbanisation, digitisation and sustainability, energy efficiency standards, technical memorandum, guides and certification, the drive to net zero, energy management and analysis, and what is a digital twin and how to achieve this through ABB ability. How energy is used today. Just going to have a little quiz to just say, give your thoughts on what you think the ratio of wasted energy during conversion to electrical energy. Is it 30%? No, it's 40%. So 40% of energy is wasted during conversion to electricity. What do you think is the percentage of total energy wasted during conversion, transportation and processing? Is it 30%? 40? 50? 60? 60% of energy is wasted during conversion, transportation and processing. Again, as I say, it's an inefficient process which is only being improved over time. And if we look at the landscape of all the different energy sources, from fossil fuels to biomass to coal to renewables, it is a very complicated area indeed. And to reiterate, 60% of energy is wasted, and conversion to heat and electricity accounts for up to 40% of this energy wastage. How energy is used today? We're going to focus predominantly on the built environment, and as it was said here, that 40% of energy is used within the built environment, and 45% of CO2 and greenhouse gases are created by the built environment. It's worth noting at this point that we talk about carbon and CO2, but carbon is an equation looking at carbon dioxide and other greenhouse gases. And for the ease, we just called it in carbon. Okay. Also, another point to note is 30% of all carbon is embodied emissions of construction products. And 70% of carbon is created from the operational use of a building. What is embodied carbon in relation to buildings? Embodied carbon is the carbon created and greenhouse gases from extracting raw materials, transportation, manufacture of the products in the factory, transport from the factory to the site and through distribution, the construction activities to actually put it within a building. And then you have the operational carbon, which is the energy used during the operation of a product. For example, from our perspective, from an electrical point of view, a motor or a fan or a lighting system or a heating system. But you also get operating carbon, again, from some passive things like sort of concrete and steel. And then you need to also consider decommissioning of the product at the end of life, to demolish the building, take it away, and to recycle or to put it to landfill. And that whole cycle is called the whole life cycle for carbon. How embodied carbon is used in a building. Zero carbon isn't really zero. As you can see from this little chart, Over time, buildings will become more efficient and the sources of energy will become lower carbon. However, the embodied carbon emissions will remain largely unaddressed. Good example of this situation is with an electric vehicle. Many people are considering buying an electric vehicle because they think it will be sustainable, it will reduce its carbon footprint. However, unless you go and source your electricity to charge the vehicle from a sustainable supply, will that electricity you use be really zero carbon? And if you look at the actual manufacture of the vehicle, from its embodied carbon, as much energy and carbon is produced during its manufacture than a traditional internal combustion engine. And there's a recent report made that you would have to drive at least 60,000 miles using sustainable energy to bring the carbon back down to the same on par with the internal combustion engine. So when we say zero carbon, we need to look at operational carbon and embodied carbon. Within a building, look at embodied carbon per element, and this gives percentages for a medium-sized building. As you suspect, the big carbon users, the embodied carbon users, are the superstructure and the substructure, where you've got steel, concrete, bricks. Another interesting point is for the facades and internal finishes. And the bit that we're really interested in is the mechanical and electrical services, which account for 4% typically of the embodied carbon within a building. Most people will understand the building regulations in the UK, Part L, which gives energy efficiency standards and metering requirements within new and refurbished buildings. According to Part L, dBs exceeding 50 kilowatts need to be measured and monitored, and mechanical loads between 10 kilowatts and 50 kilowatts. And then you have unmonitored small power. The interesting thing in this little chart is that in commercial buildings, 36% of operational energy is used in unidentified applications. And the same applies to residential buildings. 3% of operational use is used in unidentified applications. So what if we could identify those areas where the energy is being used and maybe take some actions into reducing that? Again, that would improve overall efficiency of the energy used within a building. We're now going to have a look at some megatrends. There are 5 key megatrends going on in the globe today. There's the shift in global economic power, demographic shifts, accelerating urbanisation, the rise of technology, climate change and resource scarcity. And within this presentation, we're going to look at the bottom 3. Urbanisation, as I said, it's a major global megatrend. Again, our future is set to be urban. Whether that's going to be the case following COVID, but the general trend is that we are moving towards an urban civilization. And again, today, more than half the population live in urban areas, and 90% of this urban population growth will take place in Africa and Asia. Rapid urbanisation is placing huge demands on infrastructure, services, job creation, climate and environment, and cities are estimated to occupy 2% of the Earth's surface. As I said, 1.5 million people added to the global population every week. That is a staggering statistic. In the UK, we're similar trends to the rest of the world. The estimated population in London is 8.7 million, 13% of the UK population. 81% of the UK will be living in urban areas. The over 65 will represent 20% of the population by 2030, becoming one of the largest consumer groups with increasing healthcare needs. And the southeast of the UK will grow to become the second largest region after London, accounting for over 15% of the UK GDP. Digitalisation. Digital change is constant, global and fast. Emerging technologies, global megatrends are colliding to disrupt both business and society. We've all seen the changes in the way we work and the way we shop and the way we interact with each other over the last 7 months. Who would have thought we'd be delivering all these seminars virtually, as in 8 months ago, we were doing it in person in a conference centre or in an office somewhere. The digital revolution has no boundaries or borders. I could be delivering this presentation to you from anywhere in the world. Cloud computing, big data, Internet of Things, artificial intelligence, Industry 4, BIM, e-commerce are all phenomena which are disrupting how we design, manage and use buildings. Sustainability. Again, we talk about sustainability a lot. What is sustainability? Definition: a process or state that can be maintained at a certain level for as long as wanted. Another definition is a state or a development that meets the needs of the present without compromising the ability for future generations to meet their needs. And as we live in a growing planet with a growing population, using more and more resources, we need to think sustainable, and all our developments need to be sustainable. Sustainable developments can be thought in terms of 3 spheres. You look at the Venn diagram to the right, looking at the environment, economy and society, and if they're all in balance, we create a bearable, equitable and viable situation and a sustainable state. Now going to look at the standards. IEC 60364-8-1 2019, Low Voltage Electrical Installations Part 8-1, Functional Aspects of Energy Efficiency. This document provides the requirements and measures and recommendations for the design, erection and verification of all types of low voltage electrical installations, including the production and storage of energy for optimising the overall efficient use of electricity. In the UK, we have the 18th edition of the Wiring Regs, or BSEN 7671 2018. There's a new Part 8, Section 801, Energy Efficiency, which will be taken from the IEC standard. And the requirements of the proposed new section aids in meeting the requirements of Part L of the Building Regulations. There's another important standard with regards to carbon, is BSEN 15804 2012, an amendment in 2013. This gives guidance around core products category rules relating to environmental product declarations for construction products. All construction products have to have an environmental product declaration, and we see this the most likely repository to list embodied carbon of particular construction products. We also have Part L of the Building Regulations, England and Wales, Conservation of Fuel and Power, raising the energy efficiency of buildings, ensuring that energy efficient fixed building services are installed. And this applies to new and refurbished buildings. Interestingly, there's a 2020 amendment which will look at switching from using CO2, carbon dioxide, as the primary measure for building performance to primary power. The other major change is a fabric first approach. Rather than relying on using sustainable energy, we're looking at the whole holistic approach to the design of the building to make it energy efficient by design from day one. We're now going to look at technical memorandums and guidelines. The first ones are from CIBSE, Chartered Institute of Building Services Engineers. They have a number of technical memorandum, which are listed here, which cover sustainable, environmental and energy efficiency standards and recommendations. And they also published Guide F, Energy Efficiency, and Guide L, Sustainability, which was recently updated in 2020. There is also the RICS document, which is the methodology to calculate embodied carbon and materials, and it gives guidance on how to calculate cradle to grave embodied carbon emissions for projects in the UK. And then we have an example where we have industry and segment specific technical memorandum, and this is the Department of Health issue their own guidance for energy efficiency within healthcare facilities in England. And there'll be many more of this type of document developed over the coming months and years. We're now going to look at certification and the key certification around reducing carbon and increasing efficiency and sustainability. The first one we're going to look at is ISO 50001 2018. Again, this is to enable organisations to establish the system and processes necessary to continually improve energy performance. This is predominantly aimed at large organisations and manufacturers and process users, and ABB indeed themselves are looking at taking this accreditation for our manufacturing plants. We then look at LEED, which is Leadership in Energy Environmental Design, developed by United States Green Building Council, an international green building certification system, providing third-party verification that a building or community was designed and built using strategies aimed at improving the performance across all the metrics that matter most: energy saving, water efficiency, carbon emissions, improved indoor environmental quality, stewardship of resources, and sensitivity of their impacts. This standard, as I said, was developed in the US. It's very popular in the Middle East, but it's also becoming more prevalent in the UK. The next standard we're going to look at is BREEAM, Building Research Establishment Environmental Assessment Method, developed by the Building Research Establishment. Again, an international sustainability assessment for master planning of projects, infrastructure and buildings. It recognises and reflects the value in higher performing assets across the built environment life cycle, from new construction to in-use and refurbishment. And I'm sure most people involved in projects in the UK would have come across this certification and standards. And finally is the Non-Domestic Energy Performance Certificate. Okay, this indicates the energy efficiency of buildings, its fabric, its installed heating, ventilation and cooling and lighting systems, and the property will be given an energy efficiency grade between A and G, A being the best and G being the worst. The drive to net zero. Why do we need to focus on net zero carbon? A definition of net zero. A zero carbon building is a highly energy efficient building that produces on-site or procures carbon-free renewable energy in an amount sufficient to offset the annual carbon emissions associated with the building operations. So if a building will use sustainable electricity for all its energy requirements, or it will generate its own on-site. And again, there's another definition from the UK government, where net zero means that the UK's total greenhouse gas would be equal to or less than the emissions the UK removed from the environment. This can be achieved by a combination of emission reduction and emission removal. Interesting to note where the emission removal and building operations, this can also be looked at from an offsetting perspective, which we'll talk about later. Other drivers for change is the UN Framework Convention on Climate Change, aims to stabilise atmospheric concentrations of greenhouse gases. the Paris Climate Agreement from December 2015, which America withdrew from and now looking to become part of again, which is good news. And again, to look at keep global temperature rise below 2 degrees C. Interesting photograph there on the right, which shows what potentially could happen to London if we don't become more sustainable and climate change continues unabated. Okay, then you've got the EU Energy Performance for Buildings Directive 2018, and this has set a target of nearly zero energy buildings by January 2021 for new buildings in Europe. And the UK government have adopted a net zero carbon target by 2050, requiring further reduction targets initially set out in the Climate Change Act in 2008. And they also consider the World Green Building Council. All new buildings should be net zero carbon by 2030 and all buildings by 2050. So how are we going to get there? This is quite an interesting little chart. So it looks at current energy usage today, current energy supply from zero carbon energy supply, and where we need to be by 2050 to achieve net zero. We're looking at, to achieve net zero by 2050, a 60% reduction in energy demand. So not only have we got to increase the amount of net zero carbon energy we produce, we need to look at reducing the amount of energy we use. And the way to do that is by designing all buildings to be as energy efficient as possible. So this little chart here, so building designs, future trends. So I jump on my little bike and I go across to the end of this year. Currently, only 10% of new buildings are designed to net zero. By 2021, we're hoping that 20% of buildings will be designed to net zero. 40% by 2022, 60% by 2023, 80% by 2024, and 100% by 2030. That's a lot of work to be done in the next 9 years. So by 2030, buildings will be zero carbon. So that will only be looking at their operational carbon, but also taking into account their embodied carbon within the materials they're manufactured from and the systems that they operate. So how do we get there? We've got our current practices. We can use different technologies such as heat pumps, improve airtightness, install heat recovery units, improve U values of the materials, increase insulation. So we can do all these things, but that will get us so far. What we need to do is look at a full holistic approach to the design of buildings to make them as environmentally and energy efficient as possible. So that's not only from the fabric of the building, but also the building services systems that operate within them. Low energy design. Again, achieving net zero, there are 5 key areas that we can look at. You can look at reducing construction impacts, the zero carbon balance, but we're going to look at low carbon supply, low energy use, and measurement and verification. Low or zero carbon technologies. This table's been taken from the CIBC Sustainability Guide, TM38, and this looks at different technologies that can reduce carbon, and it compares its carbon dioxide savings against its cost effectiveness and local impact. The list is obviously longer than this, but there are plenty of documents that publish this that look at different systems, and you can then look at which ones with the best suited to the application. There are other systems and technologies: battery storage, energy storage, thermal storage, fuel cells and hydrogen production. We don't go into great depth about hydrogen production in this presentation, but hydrogen should have and will have a massive part to play. Inverters and synchronization, improving the quality and efficiency of the electrical systems, absorption cooling, and carbon offsetting. So if you can't reduce your carbon or remove carbon from your operation or from your embodied system completely, you can look to offset that carbon. That can be done by carbon capture, so actually removing the carbon as it is created, or paying other organisations to capture carbon, again through removing carbon from the atmosphere or planting trees or doing other carbon capturing techniques. And finally, low energy use and energy efficiency. Again, a major upgrade of the energy performance of the UK's entire building stock will be a fundamental pillar to a credible strategy to reach net zero. And there is a lot of buildings currently in the UK that do not meet this standard. So raising the minimum energy efficiency standards for rented commercial properties from EPC band B by 2035 and milestones of DSE in the lead up time. Clean growth strategy could deliver 6 billion in cost savings by 2030 and generate one of the single largest carbon saving measures. Mandatory operational ratings can successfully reduce energy. This has been demonstrated in Australia with their neighbours scheme. And public disclosure of operational energy to the commercial sector. Again, enabling organisations to learn from each other and compare and contrast their energy usage with similar types of buildings and operations. Energy savings opportunity scheme. Audits will be publicly available to mandate that businesses in the scope of the scheme demonstrate that they have acted on the energy saving opportunities identified. So not only are we looking at identifying energy savings, that actually need to actually implement them. And finally, how do we identify and implement these energy savings? We mentioned Part L give guidelines. There is also technical memorandum by CIBSA which gives guidelines as well. But as mentioned earlier in the presentation, up to 38% of energy and electrical energy is used in unidentified systems. And what we need to do is look at identifying and measuring as much of our energy requirements and usage as possible. And that would then enable us to have the data to actually optimize energy use and remove inefficiencies. And at the same time that we can do that, because of the interconnectability of devices, you can also pull out secondary data for sustainability and maintainability from the operation of these connected devices, which I'm going to hand over to my colleague Richard, who's going to go into more detail about how you achieve this and look at some of the systems and devices that you can use. Over to you, Richard.
The next section covers energy management and verification, and we're looking at how ABB is trying to help customers in their low carbon journey. So we're looking at measuring, monitoring and the management of energy, and really we're trying to optimize the performance of the facility, ultimately to reduce the energy consumption, which again leads to low carbon efficiency and productivity. So when we look at the entire energy generation system, today, if we look on the left-hand side, we can see the energy generation system. We're really based on a centralized generation of energy. So we're looking at oil, gas, coal, and centralized power stations. So this is all shown on the left-hand side. Over the next 25 years, if we look at the right-hand side of this slide, you can see that we're moving to a more decentralized energy generation system. So we start introducing renewables, wind, hydro, geothermal and biomass. There's still a large proportion of oil and gas derived from fossil fuels, but they are diminishing in the whole grid. If you look at the middle of the slide there, you can see that it says grid balancing. And as you can imagine, once we start to introduce all these localized and decentralized generation, it needs a lot of control, monitoring, a significant requirement in terms of the technology required. If we then start to look at further down the line in terms of electric vehicle charging, we look at plug and play, smart appliances. Again, this introduces more complexity in terms of control and monitoring of energy use. So if we look at a typical distribution scheme, if we've got here past, today and the future, in the past, we've primarily focused on looking at local monitoring. And as you can see, the part on the left-hand side there, if that was a distribution board or a main switchboard, we've only really picked up data from the incoming side and at very sporadic points. Today, we can split the distribution down into 3 sections where we look at advanced power monitoring, we have some basic power monitoring, and at the final distribution, we have some energy monitoring as well, but only focused on active energy. There is local remote monitoring, so we collect the data, typically look at it locally, and there is some cloud management as well. In the future, where we'd like to be, is we're effectively monitoring every consuming point throughout the switchgear. So as we can see on the right-hand side there, the monitoring, metering, and ultimately collecting this in a cloud-based system. So this will allow us to interrogate all the data very easily, and also the data is readily available to lots of other consumers as well. So if we focus on where we are today, and there's a recommendation here from IEC 60364-8-1, and it also follows TM39. As you can see, when we look at the advanced power monitoring and network performance section, there are a whole raft of parameters that we are monitoring today. Everything from power to power factor through to THD. If we look at the very bottom end in terms of final distribution, we're only typically looking at active energy. And then in between, in terms of basic power monitoring, we've got a mixture of the two, and such as power, voltage, current, and power factor there. I think the whole general take on this slide is that we're doing a relatively good job today, but it can be improved moving forward. So how can ABB help customers on their carbon journey? If we look at the bottom right, we've got standard metering devices that many of you probably know today. And these can include everything from multifunction meters to sensor-based energy management, to even looking at fuse protective devices as well. And this data is readily available and can be fed back into a data management system. If we look at the top right, you may notice here we've got devices now with embedded metering. So these are devices that in the past typically weren't intelligent. Today we've got items such as Emax-2 air circuit breakers, XT molded case breakers, even things such as ATS switches now can all be delivered with embedded metering. So it makes collecting data a lot more readily available in terms of the distribution system. As I said before, we've even got devices that you wouldn't expect metering on, such as fuse protective devices. We can even monitor that today. So hopefully leading towards that future where we can pick up data across the distribution network. The first example here is showing a Greenfield installation or a new installation. And at the design stage, you can see this is relatively easy to achieve. A lot of the components shown on the left-hand side will be already embedded into a new design. So we're looking at air circuit breakers, molded case breakers, UPS systems, and integrating existing metering systems as well. And what we can do with that, as you can see by the red dotted line, is it can all be integrated, say on a Modbus system, and taken back both to local monitoring and to a cloud-based platform. ABB, again, can help with all these devices. We've got added devices such as eKIP hub gateways, and we have a cloud-based system called ABB Ability, which you may have heard of in the past. And this is the central place where the data is held. So if we look at the second example, such as a brownfield installation, this will be an existing installation. ABB does perform a lot of work trying to put intelligence into existing buildings. And as Nigel had pointed out earlier, it's very important that we try and get as much energy efficiency out of existing building stock as well. So when we look at the design here, we've still got circuit breakers in there, but we're adding intelligence such as metering. If you have a look on the left-hand side. And also we can add other control mechanisms at the circuit breaker level. Also at final distribution, we can add intelligence through sensor-based technologies. We would then connect that back in a very similar way as to the previous example through a Modbus network. And we can look at the data locally and again on a cloud-based platform. And we would again utilize devices such as our eKIP hub and the ABB Ability Cloud platform. That will allow you to interrogate the data on an existing installation. As I touched on earlier, devices with embedded metering are now the driving force between a lot of metering devices in the market today. So it's not just standalone metering, it's devices that can give you a lot of data embedded to it. So if we're focusing on Emax2 and Tmax XT, those are a range of ABB circuit protective devices. And as you can see from the figures there, very accurate in terms of class 1 measurement, 0.5 accuracy on current and voltage, 1% accuracy on power and energy management. And we can also introduce other performance factors such as harmonic analysis, and all with the ability to centralize this in the ABB Ability Cloud service. Again, picking up on the analysis, as well as looking at the actual energy consumption, we can look at many other parameters associated with the electrical network, such as harmonic analysis. We can look at average values and plot those. We can look at disturbances in the electrical network, such as voltage interruptions, spikes, sags, swells, and also voltage imbalances. All issues which affect the efficiency of the electrical network and the devices associated with. So when we look at the system architecture, and ABB brands this as a beyond connected, there's a slide here where we're showing on the right-hand side the sub and final distribution, and on the left-hand side we're showing the main distribution. So if we look at the right-hand side, as you can see at the bottom, we can monitor right down to circuit breaker level. So we can look at individual outputs of where that energy is being used. We can centralize that data into modules and through metering as well, as you can see through a panel there, and we can send that data back either to a third party BMS or SCADA system, or back to an ABB web server device. We can then feed that in to the main distribution, And as if we look on the left-hand side, you can see the circuit breakers there that are doing the metering and the monitoring and the other advanced power features. That can be centralized back and also sent to either an ABB cloud-based system, again to a web-based web server system, or to a third-party data collection service. We're able to cover off the data collection across the whole main distribution, sub-distribution, and final distribution. So at this point, I'm going to hand you back to Nigel, who will take you through the rest of the presentation.
Okay, we're now going to look at digital twins and utilising ABB Ability platform. You may or may not have come across the concept of a digital twin. Digital twins have been used in industry and aerospace and automotive for many years, and it basically looks at and creates a digital copy of the real thing, so you can actually measure the performance. People may be aware, like say in Formula One, the cars are fitted with sensors, and it gives real-time data back to the team in the pits, and they can see how the vehicle's performing, and they can do minor tweaks to that during while the car's being used, or when it gets back to the thing to improve and optimize efficiency and performance. The same approach can be done with a building, and digital twins could help us deliver the many challenges we face today. As we mentioned, the megatrends: urbanisation, population growth, climate change, escalating infrastructure costs, and sustainable development. And buildings can benefit from the implementation of a digital twin. And as before, it has already been tried and tested in the field of manufacturing. It can give us energy and resource consumption and efficiency and management, predictive maintenance and asset management, occupant comfort and enhancement, occupant use, efficiency and space management, enable us to do what-if analysis. What if we change the occupancy levels? What if we change the floor plate of an office building? What if we change the operating temperature or humidity by certain degrees? We can do that within the digital twin first before actually putting it into the real building. Again, you can use the system to evolution and enhancement of the buildings, and also taking that information back and put into later designs and give you closed loop design. And ultimately, it will give operational cost reduction, but the ultimate payback on that is be able to use less energy, optimize carbon operationally, optimize carbon from an embodied carbon point of view, and ultimately reduce carbon. So what is a digital twin? We've got there, most people are familiar with building information modelling, where you do a 3D geometric design of a building, looking at all its systems and the fabric of the building. We mentioned earlier these connected devices. If we look from a building services point of view, we have got meters, we've got sensors, and we can take that now down to final circuits. We can also embed sensors into fans and into motors. And they can also fit sensors that measure in natural light levels, oxygen levels, CO2 levels, occupancy. And you can take all that information and you pull it back through building system or building energy management system. And we put that through into an analytical programs. And we can actually look at what we're actually generating and how we're using that building. Using the integration in the analytics in the algorithms, we can actually then look at optimizing that building and the performance, and you create a digital twin of that building. Again, we mentioned earlier, it'll give you predictive maintenance, so the sensors will be giving you feedback on condition wear, a condition as a circuit breaker has been tripped, is there bearings worn on a motor, is it working at its optimal efficiency? You can look at the whole operational cycle, you can look at energy uses and do what if analysis. Currently, there is no sort of single design or software that can do a full digital twin, and it's more likely that it'll be an ecosystem of digital twins, each little digital twin doing its own little specific job of the building. As I mentioned, ABB ability will be able to give you full control and visibility and optimization of your energy system. So we can look at your electrical systems, we can look at your heating systems, your ventilating systems, and all the plant within it and feed that back. So you could actually create a digital twin of your building services system utilizing ABB ability. So what does that give us? So we have all these buildings connected, looking at monitoring all the systems. So that brings it through ABB ability. One of the key areas is that we should be looking to share our data and learn from each other to improve and optimize energy usage. So you've got an example on this particular slide. There's 3 separate buildings, each one building services systems are all connected back, and through ABB ability, we're looking at energy, asset security and comfort. All those systems are being handled and managed by the ABB ability platform. So utilising all that data from those 3 real buildings, we've now created 3 digital twins of those buildings, linking off the BIM data and the BIM models, taking it through artificial intelligence. We can then improve and look at overall efficiency and optimise the use of the energy within those buildings. Again, that's great on a single building, as we mentioned, an ecosystem of digital twins. And if we all shared that information and collected, we can then start moving towards smart cities. And then you start not only linking your buildings, but also the infrastructure and planning requirements back to generation. So you have a full scalable smart city solution. But with ABB ability, we can look at that at a level from a building or multiple buildings. And with ABB ability, again, there's the key areas that you need to do to reduce your carbon. You need to know, you need to assess, inform and measure what you're doing with your energy. Do more, monitor, control and manage. Do it better, optimize, predict, simulate. And together with other building operators or with your own developments, collaborate, advise and rethink how you're doing using your energy and how you're using your systems. And all this can be done through the ABB ability platform. Give you a typical example of the dashboard. So this looks at energy management, energy conversion, energy cost, energy monitoring, audit summaries, real-time power, power demand, power generation, peak monitoring, performance indications, ENPI monitoring and energy monitoring. There's also another dashboards that look at asset management and asset monitoring as well, looking at condition and wear, and also looking at event management and monitoring as well. All this is straight with ABB ability, which is to say it is digital twin ready for your energy management system. And just to prove that ABB do try to walk the talk, ABB have committed to become zero carbon, and we're following the European directive where ABB are hoping to have all their operational facilities zero carbon by 2050. And we're doing that by looking at building renovation, improvement programs, putting in energy performance in old building to optimize our energy use. You know, if you can measure it, you can change it, you can make it better. Monitoring energy performance of the buildings and also support rollout of e-mobility infrastructure. And one of the key areas that ABB are currently doing, they're currently transferring the whole entire fleet to e-mobility vehicles. So again, we are practicing what we preach. And again, this is another little small example of a project that we've been involved with. It's the tallest wooden building in the world. Again, mission to zero. Wood and timber is a very carbon efficient material. It's actually a carbon capture material. So it's taking carbon out of the environment and actually capturing it, and they're then being utilised within the building. An ABB solution on this particular project was the using ABB Ability to provide an electrical management system, measuring all the building services requirements, and again ensuring they optimise their optimum efficiency. Okay, just like to thank you. We've now reached the end of the presentation, and we're just going to look at the areas that we've covered. We've looked at how energy is used today. We've looked at some of the global megatrends and assessment of energy efficiency standards. We've looked at and give us an understanding of the factors driving net zero and the carbon agenda, and subsequent developments of energy management and verification technologies, which was looked at in great depth by my colleague Richard Quilter. And we've also touched on digital twins and how they can help drive the net zero carbon agenda, and ultimately link together to create smart cities where the whole city is working together to reduce carbon emissions and to become net zero. Just like to thank you for listening to our webinar on decarbonisation of buildings. And should you have any queries or questions or require further information about ABB's portfolio of products and solutions, please feel free to contact me. You can get me on my email, which is nigel.thomas@gb.abb.com. Thank you again.